Well tests in fractured rock are important for characterizing the performance of wells. There are a variety of applications for wells in fractured rock aquifers. They can be used to provide water for a municipal supply in some cases, or for domestic supply. Perhaps you need to dewater a region for doing construction, and there are several different applications for environmental work to control plume, recover contaminants, or perhaps do remediation. And all of these applications share the need to be able to characterize what the well will do. So when you pump the well, what will the flow rate be for a given drawdown? What will the drawdown be out away from the well in the aquifer? So the simplest approach to doing this is to just ignore the existence of the fractures altogether. If the fracture spacing is small relative to the size of the aquifer, then maybe you can just say, well, I'm going to forget about the fractures being there and just assume that this is a porous media, and I'll just use an equivalent porous media to characterize them. And so instead of having a system like this where there are fractures, these discrete features, and a matrix in between them, I'm just going to lump all the effects of those fractures together and have a single value of hydraulic conductivity and storativity that characterizes this aquifer. So if this is the case, then we might just assume that the flow is radial to the well, the aquifer is uniform, all the water that's pumped out by the well is released from storage. And if those are true, then we could use the Tice or the Jacob simplification of the Tice analysis to analyze the results. We could plot the drawdown from a monitoring well as a function of the log time, and we might expect that this kind of a plot would occur where the slope starts out gently at first and then increases, and you have this part of the curve where the semi-log straight line forms. And we know from the Jacob analysis that the transmissivity is inversely proportional to the slope of that semi-log straight line, and the intercept is proportional to the slope, where this guy right there, we called that in the Jacob analysis, we called that T sub 0, and that was going to be proportional to the storativity, and the slope here is inversely proportional to the transmissivity. So the same things that we saw that were used and developed for porous aquifers, for discrete layers, we could use to characterize fractured aquifers as a first cut. Okay, and similar thing with slug tests. That as a first cut, we just ignore the existence of the fractures and assume that the aquifer is uniform, and then we can do the slug test and use the Vorslev or perhaps Bauer-Rice would be better to give us a little better control on the geometry, or perhaps other analyses of slug tests that are meant for uniform porous aquifers. So that would be the first cut, but there are many other different conceptual models that can be used for characterizing well tests in fractured aquifers, and here's a list of some of them. The one that I just spoke about was called the equivalent porous media, where we've assumed that it's homogeneous. We could have a variation on that where we still assumed that it was equivalent porous media, but it was homogeneous and anisotropic. So this would be homogeneous and isotropic. That's what I said before, because there was just one value of hydraulic conductivity. But we could also assume that it was anisotropic and that the hydraulic conductivity was directional. This conceptual model here, the dual porosity conceptual model, assumes that you have a fractured system like this, and the fractures cut through a matrix of rock that has a porosity to it that can be appreciable. So if this was a sandstone, for example, then it may have quite a substantial porosity, and so the fractures themselves would have one porosity and the matrix would have another porosity, and there would be exchange of water between the fractures and the matrix. And that can be important for the pressure response during well testing, as well as for contaminant transport, where the contaminants are transported from the fracture to the matrix, or back and forth. So another conceptual model that could be important around here is a situation like this, where here's the water table, and this is saprolite, and there's a transition zone to fractured rock. So this is fractured rock down here. This is saprolite, and we have a well here. And so in this case, this is no longer homogeneous, because the fractured rock is here as one layer with one set of properties, and then the saprolite is here as another layer over top of it with a different set of properties. So in this conceptual model, we can analyze the results of pumping tests and try to characterize the properties of both the saprolite and the fractured rock. Boundaries are also important. Stream boundaries, for example, they'll affect the characteristics of a pumping test. In fractured rock, if there are faults that offset blocks of different permeability, then that can be an important characteristic as well. Vertical fractures, fractional flow dimensions, heterogeneous equivalent porous media, these are all other conceptual models that are used to represent fractured rock. And hydromechanical well tests, in this conceptual model, fractures, if this is a fracture and it's loaded by some pressure, and say that pressure drops due to pumping, then the fracture aperture actually changes and shrinks. So the fracture walls become closer together, and during hydromechanical well tests, this change in aperture, the displacement, is measured during the test. So as it turns out, this is something that we've done a good bit of work on here at Clemson, and the strategy is to measure the pressure or the hydraulic head during the well test, and also measure the displacement during the well test with some specialized instrumentation, and then you analyze both the hydraulic head as well as the displacement during the analysis part of the test. Packers are an important aspect of well testing in fractured rock. These things are inflatable glands, inflatable sleeve that can be expanded to seal part of the borehole. So here's an example of an uninflated packer. This is a rubber sleeve right here, and when it's inflated with air, it expands out, and the idea is that it would expand out and push up against the wall of the borehole and form a seal right here. That allows the one part of the borehole to be isolated hydraulically from another part. There are two main configurations. One is where fractures or packers are used individually, and another where there are two packers that are used together to straddle a particular interval. That allows you to isolate the interval between the two straddle packers. So here are some configurations for packers. This is a straddle packer here that's isolating this permeable, well, it's isolating, I guess it's supposed to be isolating this blue water-bearing unit. Although it seems like the packers would want to be brought a little bit closer together so you wouldn't have this one leaking in there. But nevertheless, here's a set of straddle packers that are isolating this permeable interval, and here's a single straddle or single packer that's put here at the bottom of this this part of the hole to basically isolate this upper part, this upper permeable zone from whatever is down here. And similarly, a single packer is used to isolate this lower part. So here's the pump, and presumably now we're pumping, or this is an aquifer. It looks kind of like a limestone aquifer perhaps, and we're pumping out of this part of the aquifer and isolating it with this packer from this upper part. So packers allow us to test individual parts of the borehole, characterize their hydraulic properties. Here's an example of some data that was obtained from LAR4 at the lower well field. We conducted about 15 packer tests, maybe 20 packer test as a function of depth in LAR4, and we measured the transmissivity. Here's transmissivity and storativity. These are the common properties, and we can see that they vary by quite a lot as a function of depth along the borehole. There are three main permeable intervals. This upper permeable interval here, all the three intervals are hatched. So this interval here, and then this lower interval. And they're identified with these multiple packer tests that give different properties. You can see, for example, that in this upper fracture zone, that the transmissivity is right around in here, and then when you get down below that, you have lower transmissivity. Get into this middle fracture zone, it jumps up again, and then you've got this zone of low transmissivity. And then this one right here, this is kind of cool. This is at the bottom of the borehole, or near the bottom, at about 50 meters depth, and this log right here, these individual tick marks are fractures that are observed in the video log. So you can see that down here at 50 meters there's just one permeable fracture, but it has a fairly high transmissivity. Up here the fracture density is much higher, and the zones are fairly transmissive, but you get about the same result for the transmissivity at the lower fracture. And we also went and calculated the effective hydraulic aperture. That's what's shown on this plot in microns, and you can see that these permeable zones have an effective aperture of about 500 microns. Okay, so one thing that is important to recognize is that when you inflate packers, you have to use the correct pressure. Packers expand when they're pressurized, and the pressure that a packer feels is really the difference between the pressure that inflates it and the pressure that contains it on the outside. So as you put a fracture down in the well, it feels the hydrostatic pressure. This contains the fracture, or contains the packer, and so in order to get the packer to expand, you have to put first enough inflation pressure to just counteract the hydrostatic, and then you have to increase the pressure above hydrostatic to get the packer to expand out. So the hydrostatic pressure is obtained by measuring the depth to the packer here and the depth to the water table here, and you take the difference between those two, and that gives you the depth from the water table down to the packer. So you take the product of that and the unit weight of water, and that gives you the hydrostatic pressure. So here's the formula where that's the unit weight, there's the total depth of the packer, and there's the depth to the water table. And when you do this, you have to use the correct units. So if D and A are in feet, then gamma, the unit weight, would be in psi per foot, or at least that's a convenient unit to use, because then you'll have the hydrostatic pressure in psi. So the packer differential pressure for the low pressure packers that we're using, 35 psi would be a good packer differential pressure. And so the total pressure that you're using to inflate, this would be the pressure generated by the air compressor at the ground surface, is the sum of these two, the hydrostatic pressure and the differential pressure used to inflate the packer. I should point out that the packers that we're using are quite low pressure. That's a very small pressure for packer inflation pressures. We have another packer in the trailer that is typically inflated to about 500 psi, and when you do that, you have a much tighter seal on the borehole, and you can generate much higher pressures within the packed off interval. So when we do slug test here, because we only have 35 psi of pressure on the packer, then we can only have a small fraction of that pressure be applied to the the zone between the packed or between the stratal interval. So we do a slug test, and these are pretty modest slug tests. The slug, the total displacement on the slug is maybe well, let's say it's 2.4 feet. That would be equivalent to 1 psi. So we have 1 psi of pressure difference here between the packers, and we have 35 psi of pressure inflating the packers. So these packers should remain sealed against the borehole wall in this case. But if we were doing other tests that required higher pressures, then we would need to go to a higher pressure packer. So one thing that has been recognized is that the fracture geometry, or the type of fracture networks that form in these crystalline rocks, like the ones around here, tend to form zones. So the permeable fractures are connected to other permeable fractures and form a network, but the network has a finite size. And so you have a cluster of fractures that are connected, but it's kind of enveloped in rock that is relatively unfractured. So there's a test site that's run by the USGS up at Mirror Lake in New Hampshire, and they did some tests there and found that at their site there were 4 fracture zones shown here with these color blocks. So that purple zone right there is one of these fracture zones. They're roughly flat lying, and here's the scale in cross section, 30 meters. So it's maybe 100 meters, maybe a little bit bigger than that across. And you can see this purple fracture zone, it's got this finite size, but it's not really connected to this other purple one. And so the way you can tell that is because some of the wells intersect fracture zones, and you have multiple wells in the same fracture zone. So when you pump one, the other one that's in the same fracture zone responds quickly. But other wells nearby that aren't in the same zone, they don't respond, or they respond much more slowly. So you can kind of see how this is working. Let's take these wells right here, wells 7, 5, and 8. As you follow them down, you can see that well 5 is in the purple fracture zone, well 8 is in the green one, and well 7 is in none of them. And so even though these wells are quite close together, they would have different hydraulic responses during pumping tests because of the different fracture zones that they're intersecting, or that they're not intersecting. So if you look over here, this is a plot of drawdown as a function of time, and this has a drawdown in a log scale, and this is drawdown in a linear scale. So this bottom plot is the type of plot that we've seen, where you can see that the drawdown is going up like this, and then it reaches a semi-log straight line right here, and then it's rolling over in response to as a result of some other effects. And what you see is that some of these responses cluster together, these guys, these guys, these guys, but the piezometers are similar to each other, but they're different than other piezometers. And so the explanation for this was that there was this kind of behavior going on, that there were this complicated connection of different fracture zones that was resulting from this kind of a configuration. So as it turns out, other people have come along and done similar kind of work and found similar kinds of things. And so a typical characteristic that we might expect is that when we have wells in fractured rock, some of them may be connected by intersecting a similar fracture zone, but these fracture zones are kind of discrete, and we might have some wells that don't intersect the same fracture zone as others. And so we might have this kind of zonal effect, and it would be really good if we could use a pumping test to try to get a handle on this. Well, as it turns out, I mean, that's what these guys are doing here. But as it turns out, there's a little bit of well, we need to kind of take a step back and look at things conceptually. Okay, because if we just plot drawdown as a function of log time, then we can have different responses here. And this actually is what you would get if the well, you could get something that looks like this if you have just piezometers at different distances. Well, actually, I mean, let me rephrase that. You could have a different response where you have drawdown plotted as a function of log time from piezometers that are plotted at different radial distances. So just because that they are you have a different response doesn't mean that the piezometer is in a different zone. So what you do to compensate for this effect of piezometers at different radial distances is that instead of plotting the drawdown as a function of log time, you incorporate the radial distance to the aquifer or to the piezometer in the plot itself. Okay, so what I've got here just shown schematically is the drawdown from 4 different piezometers at different radial distances, and that's this number here. And so some of this difference in the plot is a result of being in a different zone, but some of it is a result of being at a different radial distance. You know, when the piezometer is at a further radial distance, the drawdown will be less. That's what you would expect to happen. And so to sort out this difference, we plot it like this. And what happens then is that we've got these two curves grouping together, the piezometers that are shown here, and these two that are grouping together. And so what we might infer then is that these two piezometers intersect the same zone, same permeable zone, and these two intersect the same permeable zone. Okay, so that's pretty cool because now we can try to get a handle on what the characteristics of these two permeable zones might be. So here's how we would go about doing this. Well, actually, I'll show you how to analyze it first, but let me just try to clarify what's going on in that plot, okay? So here's what we've got. The basic data that we would have is the depth to water as a function of time. So here's the piezometer, and here's the water level, and we're up here measuring depth to water below our mark on the casing. Okay, so that's depth to water. And now we're going to do a test, and we're going to drop the water level to there. And this is the drawdown. So what we want to do is plot the drawdown as a function of time over r squared. That's the plot that we saw on the previous slide. So drawdown will be done like this. It's the depth to water minus the initial depth to water. So that guy right there, that would be depth to water 0, the initial. Okay, and so if we have something like this, we've got our data set up in a spreadsheet, say, or at least we can just think of it as at this time we have this drawdown and so on. Then we convert the data from depth to water to drawdown by simply subtracting off the initial depth to water. So that would be what we would have here in this column. And then in this column, we just simply take the time that we measured. Well, this would now be elapsed time, so this is since the pump was turned on. And we divide that by the radial distance to the piezometer. So if here's our pumping well, and here's the piezometer, then we have some radial distance there, and we take that radial distance, square it, and divide the time by that, and that's what's in this column. Okay, so that's how we change the data from our field data to what we would plot to generate the plot that we saw on the previous page. Now we've got this plot with these two zones identified, zone 1 and zone 2. Okay, so what do? Well, we want to get the properties of these two zones. These are different fracture zones, and at least that's what our interpretation is. So we go back to the Jacob analysis, and it says that the slope is equal to that term, so we can solve that for the transmissivity and basically just do the same thing that we were doing previously with the Jacob analysis. Then to get the storativity, what we do, remember what we did before was to extrapolate back and determine t sub 0. So we would fit a straight line here and go back and determine t sub 0, and then we use that t sub 0 in the calculation of the storativity. Well, when we have the data plotted up like this as t over r squared, then we simply get the intercept here, and that intercept is t over r squared sub 0, that thing right there. And then we have just a modification of the Jacob analysis shown right here. We substitute in the value that we get from the plot, do the calculation, and that gives us the apparent storativity for that particular zone.